So that's great. We executed instructions at deadbeef, but now you're going to say, OK, that's great, but it's not going to always be the case that someone magically puts bad instructions at deadbeef. I don't know about you, but when I'm writing a piece of C code, I don't stick a piece of malware in there and say, oh, I'm going to leave this here for the attacker. We don't do that. So how is the attacker going to execute instructions that they want to execute if they aren't already in memory? So in this case, we were nice to you and we said, we preloaded some bad instructions in deadbeef. But that's not always true. So what if the attacker wants to execute instructions that don't live in memory? What do they do now? So one thing we could do is, well, OK, there's a note about null bytes. I forgot that was there, but there it is. But something we could do is, if we don't have the malicious instructions already in memory, we can put them there ourselves. What does getAs do? getAs says, go into memory and write whatever the hell you want. So instead of just writing A's and addresses, we could also write the actual instructions. So for example, the attacker could say, I want to execute these malicious x86 instructions. So the attacker will pull out their assembler, convert these instructions into ones and zeros. These are ones and zeros. I can write them into memory. They correspond to ones and zeros. They're bytes. So instead of just writing A's and addresses, the attacker can write actual instructions into memory that they wrote themselves. And then they can cause the program to execute these instructions. Go to this address, execute these instructions that I wrote into memory. And these instructions can do whatever you want. They can delete all the files. They can run another program. They can send spam emails, whatever they want. But a really common thing that attackers will do with this malicious program is they'll spawn a shell. And what that means is it opens up a terminal and lets the attacker type whatever they want. So you can imagine, let's say that vulnerable code was running on a top secret server somewhere, and I inputted an attack. And when I input the attack opens a terminal, and now I have a terminal on that top secret machine. So I can type whatever instructions I want, and that compromised machine will execute them. So this code can really be any arbitrary code that the attacker wants to execute. But a common thing that attackers want to do is they want to open a terminal, because that gives them full control over that computer to do whatever it is they want. And people sometimes call this shellcode, because it is code that spawns a shell. Shellcode. Okay, it's a very creative name. So that's what it looks like to write malicious code. So the punchline of this slide is, if the attacker or if the person who wrote the program doesn't magically give you some malicious code that you can execute, you can also input malicious code yourself. So this is what we're going to try coming up next. Unless you have questions before then. OK, so we now know that we can write malicious code ourselves, put it in the program, and cause the program to execute that malicious code. So let's see what that looks like and try to put together the whole attack. So here's what we're going to do. First, we're going to find the vulnerability. We're going to try and find where in the program the attacker can write out of bounds. We are going to write the shellcode into memory. The shellcode wasn't there. We are going to write it there ourselves. And then we're going to overwrite the RIP. That's the address that tells us where to go after the function returns. It currently holds the address of some nice function. We're going to replace it with an address. The address of what? The address of the shellcode we just wrote. So in other words, we're telling the program, when you return, go to this address. And what did I put at that address? I put the shellcode that I just wrote. So that's what we're going to do. We're going to do all this in a single step. And when the function returns, it's going to say, I'm done. Where do I go? I look at the RIP value that holds an address. I go to that address. And at that address, oops, I found shellcode. And I start executing malicious shellcode, and the attack works. So that's what I'm going to try to do. I'm going to write some shellcode and then force the RIP to point at that shellcode. So when the function returns, I go execute that shellcode. So here's what it looks like. This is the same stack as before, the same code from before. The only new thing is I have annotated the diagram to tell you the addresses in memory. So for example, the SFP of vulnerable, that's some value living in memory. It lives at address BFFFCD54. That's what the picture says. Or name. Name starts at address BFFFCD40. That's all the diagram is telling you. So Let's say you have some 12-byte shellcode. Someone has told you, I want to execute this shellcode. It doesn't already live in memory, so you got to put it there yourself. And the question for you is, what do you want to write into memory? So I want to get shellcode into memory. I want to change that RIP. Where do I put all these different things that I want to put into memory so that they all line up properly? And when this function returns, it's going to go and execute shellcode. So if you're on the video, take a minute and think about it. Pause the video. If you're in person, take a couple seconds. How do I put all the pieces together? OK, I'm just going to spoil this one, because we're almost out of time. So here's what I want to do. This RIP value, I want it to point at shellcode. Where is shellcode? That depends on where I put it. So there's actually lots of different solutions, but one that I can think of is I'm going to start by writing the shellcode into memory. The shellcode is 12 bytes, so it takes up 3 of these rows, 4 bytes each. There's shellcode. It now lives in memory. It wasn't there. I wrote it. Now it's there. These are 1s and 0s that correspond to malicious instructions. Now what comes next? Remember, the getAs function, it writes consecutively. The getAs function doesn't let you say, OK, I'll take a break and start writing up here again. The getAs function assumes every character that you provide, it writes it to higher and higher addresses with no breaks. So if I'm here and I finish writing 12 bytes of shellcode, I can't just drop the address right here, because this is not where the RIP is. I want to overwrite the RIP with an address. So I need to start writing garbage bytes, like the letter A. So garbage, garbage, garbage. I'll write a lot of garbage bytes. Here happens to be 12 to overflow these 3 lines in the stack diagram. And now the next thing that I write is going to clobber out the RIP. So now I can write an address. What address should I write? Well, remember, I want the shellcode to execute. So I'm going to write the address of shellcode. I put shellcode down here. The place where I put it happens to have address BFFFCD40. So what am I going to write into memory in little endian form? I'm going to write BFFFCD40. So what I had to do was I had to line up everything nicely in the stack. And now, if I execute this code, what's going to happen? Well, what's going to happen is the program is going to say, I'm done, time to return. I'm going to take this address in the RIP, go to that address, start executing instructions, and the shellcode gets executed, and the attacker has succeeded in getting shellcode to run. So that's your very first memory safety exploit with shellcode.